What is life? Where did we come from? Water is H2O, made up of 2 hydrogen atoms and 1 oxygen atom, held together by covalent bonds. The air we breathe is a mix of countless particles, along with dust and water vapor. So, what exactly makes up life? What are the essential ingredients of our being? And what was it that set us apart nearly 4 billion years ago and still separates us from everything else today? There's no doubt that people in ancient times were deeply curious about these big questions. It was the Greeks, starting around the 7th century BC, who turned this curiosity into a serious pursuit. Many Greek philosophers like Epicurus, Lucretius, and Plato spent their lives pondering the origins of life. Their overwhelming conclusion was, life comes from life. But what about the first life? What started it all? In the 4th century BC, Aristotle concluded that living things could spontaneously arise from non-living matter as long as that matter contained vital heat. He suggested that worms emerged naturally from decaying manure, insects sprang from morning dew, and eels could form from damp alcohol and rotting seaweed. As unbelievable as this sounds to us today, Aristotle's idea of spontaneous generation dominated thoughts about the origin of life for almost 2,000 years. Scientists after him came up with increasingly elaborate recipes for how life could form. For example, in the 17th century, a Dutch scientist named Jean-Baptiste van Helmont proposed that if you left a dirty shirt in a bin with some wheat germ for 21 days, live mice would spontaneously appear. Over time, though, these theories lost support. Science advanced, and explanations were found for what once seemed like miraculous appearances of animals in old trash heaps. But for smaller, more mysterious creatures like bacteria and single-celled amoebas, spontaneous generation was harder to disprove. Finally, in the 19th century, French biologist Louis Pasteur designed an experiment to eliminate any external influence on a flask filled with lifeless material, a vacuum. When the flask remained sterile, it proved that spontaneous generation was false. Matter alone couldn't create life. To this day, no laboratory has been able to produce life from non-life. Frankenstein remains fiction. Life, and only life, continues to create life. Yet today, we know that Earth formed over 4 billion years ago without life. No living thing could have survived the violent conditions of the Hadean Eon. And yet, here we are, on a planet teeming with life, in every imaginable form and function, from rainforests to deserts, from the highest peaks to the deepest ocean trenches. Life thrives. So, it's clear that at some point, between 3 to 4 billion years ago, matter somehow gave rise to life. The last act of spontaneous generation in history, the origin of life on Earth. The big questions that remain are, how did it happen, and from what? The very first life on Earth must have been the simplest kind of life imaginable. There's no way something like a mouse could have just popped up out of nowhere during the late Hadean Eon. To figure out where life came from, we first have to ask ourselves, what exactly is life at its most basic level? That's a huge question, one that demands everything modern science has to offer. In most schools, we're taught to define living things by what they do. Animals, plants, and fungi all work to keep themselves alive, grow, and reproduce. But that's not the whole story. Living things might do these things, but they're not the only ones. By that definition, some crystals could be considered alive, or even computer viruses, which are really just clever algorithms. These days, though, that's not how we define organic life on Earth. Instead, we need to zoom way in, down to the microscopic level, to see what living things are made of. The simplest forms of life today, like bacteria, have 2 key parts: a self-replicating molecule, like DNA, that carries instructions for making copies of itself, and a self-sustaining metabolism that provides the tools to do the work of living and replicating. With this definition, we capture the essence of all life on Earth. Everything is made of cells, like bacterial cells, that contain a self-replicating molecule and a metabolism that keeps them going. By this definition, viruses sit on the edge of life. These tiny structures have a self-replicating molecule, just like other living things, but they lack the machinery to do anything with it. Instead, they have to hijack other organisms, borrowing their biological factories to reproduce. Some scientists say viruses are alive, others don't, and some even think viruses might be part of the puzzle of life's origins, perhaps a middle step between living and non-living. So, the first forms of life needed two inventions, a self-replicating molecule and a metabolism. But these were no simple inventions. Our DNA, for instance, is an incredibly complex macromolecule, a long double-stranded structure made up of millions of smaller, simpler molecules, which themselves are built from atoms like carbon, oxygen, hydrogen, nitrogen, and more. Modern metabolism, built around this massive molecule, functions as a highly sophisticated organic factory where each part is fine-tuned for a specific task and depends on everything else to keep the system running. Of course, life couldn't have started with something that complex. It must have begun much more simply, using basic building blocks that were already present on the young Earth or formed for the first time in its early oceans. To uncover the true origin, we have to look back at the chemical makeup of the young Earth. Out of all the possible elements in the universe, 94 naturally occur on Earth. Each element has unique characteristics, its ability to bond with others, and the energy needed to make or break those bonds. Some elements barely react at all, while others, like silicon, react slowly and require a lot of energy to rearrange their molecules. Silicon is abundant on Earth, but it's not a great candidate for the dynamic, reactive life we know. Carbon, on the other hand, is a much better choice. It's the fourth most common element in the solar system and easily forms strong bonds with other carbon atoms, as well as with abundant elements like oxygen, hydrogen, and nitrogen. All life on Earth is built around this versatile element, combined with oxygen and hydrogen in what we now call organic molecules. In fact, during the Hadean Eon, Earth was a melting pot of organic possibilities. Sugars, key building blocks for our genetic molecules, and the fuel for cellular factories were created through cosmic chemistry and formed in the star-forming regions of the Milky Way. They floated freely in the early oceans. Nuclear bases, simple nitrogen-containing compounds that, when combined, became the foundation for storing information in self-replicating molecules, the molecular language of life's instruction manual. A repeating sequence of 4 different nuclear bases encoded all the instructions for survival, growth, and reproduction. On early Earth, these bases might have been naturally produced by primordial chemistry. Then came amino acids, essential for all life on Earth, and the building blocks of proteins, the structures that make up nearly all the machinery in cells. In the 1950s, 2 American scientists, Stanley Miller and Harold Urey, conducted a famous experiment to create amino acids from what they believed to be the composition of the early atmosphere. They started with a mix of water, methane, ammonia, and hydrogen, then ran an electric spark through it. On early Earth, similar conditions could have been created by lightning, striking from storm clouds over the planet's first mountains. The result was the formation of entirely new chemicals, including several amino acids, the fundamental building blocks used by all life on Earth. They proved that organic molecules could be created from inorganic matter. So, the building blocks of life existed, floating around as part of an organic soup in Earth's early oceans. But this alone wasn't life. These molecules had to come together in a very specific way to form self-replicating molecules and protein machinery, the keys to life. And here's the paradox. Today, most living things use DNA as their self-replicating molecule. The sequences of nuclear bases in DNA encode all the instructions for growing, reproducing, and making proteins. But to do all this, DNA needs protein machinery to read the instructions, interpret them, and create new components. It needs hands to do the work. So, proteins are needed to read and replicate DNA, but the instructions in DNA are needed to create the proteins in the first place. This is the classic chicken and egg problem. Which came first, proteins or DNA? The real answer is likely neither DNA nor proteins. Scientists today believe that another molecule filled the gap, the true prototype for the complex machinery that drives our existence and the true beginning of life on Earth. Beneath the chaotic depths of Hadean Earth's oceans, for the first time, a molecule might have successfully replicated itself. That molecule was RNA. RNA is a single-stranded, self-replicating molecule, similar to but simpler than DNA. It can replicate itself, but can also fold into three-dimensional structures, much like the protein machinery used by living things today. Scientists think RNA might have been an all-in-one molecule, capable of performing both metabolic and replicative functions in the early stages of life. This led to what scientists call the RNA world, where all biology was built on single-stranded RNA sequences floating in the prebiotic soup. Random combinations of sugars and nuclear bases came together and spontaneously bonded through chemical reactions. Some fell apart, but others remained stable and continued growing into long chains, one nuclear base at a time. Occasionally, these chains influenced their own structure, coiling or folding back on themselves. In this way, a kind of prebiotic natural selection took hold, favoring molecules that were structurally stable and mechanically useful. But RNA alone wasn't life. The RNA ecosystem was merely a fluke of chemistry, not a self-sustaining organism. Any chemical imbalance in the primordial oceans could have wiped out the RNA world entirely. Even a small puddle on the early Earth was a vast space for a fragile RNA strand. The chemicals needed for metabolic reactions were too diluted, making the chances of them interacting vanishingly small. For metabolism to truly get going, these reactions needed a box to take place in, something to separate them from the outside environment, concentrate the necessary chemicals, and allow RNA to guide the internal processes. All living things rely on such compartments, these boxes. Some organisms only need one compartment, while others have trillions. The first structures likely resembled modern cells, but were far simpler. One promising candidate for these early protocells is fatty acids. These molecules could have formed spontaneously through chemical reactions in the prebiotic soup. Their interaction with water made them special. One end of a fatty acid is attracted to water, while the other repels it. When exposed to water, they naturally organized into spherical structures, shielding the water-repelling parts inside while letting the water-attracting parts face outward. Larger spheres could easily encapsulate self-replicating RNA strands. The interior provided a protected and isolated environment where chemical reactions could occur, guided by RNA. Primitive metabolism emerged, with chemically stable configurations favoring self-preservation and longevity. From atoms and molecules formed in the stars and concentrated on the volatile surface of early Earth, massive macromolecules arose, finding ways to replicate and pass on their success to future generations. And so, just once, life emerged from inorganic matter, paving the way for 3.5 billion years and counting of life-sustaining life.